Hello, everybody. In this episode, I'll be speaking with David Rein. David is a researcher at METR focused on AI agent capability evaluation. To read a transcript of this episode, you can go to axrp.net. You can become a patron at patreon.com/axrpodcast, and you can give feedback about the episode at axrp.fyi. All right, David, welcome to the podcast.
Yeah, thanks for having me.
So I think the work that that you've been involved in that's probably best known in the AI existential risk community is this paper that METR put out with a whole bunch of authors. I think the lead author is Thomas Qua, measuring AI ability to complete long tasks. What's going on with this paper?
Yeah, so Thomas Qua and Ben West co-led the project, but basically the kind of typical way we measure progress in AI is via benchmarks. So a benchmark is a set of tasks that you have an AI system. This could be a neural network or an agent or whatever. You have it try and complete the tasks, and you kind of count up like how many of the tasks did the model succeed at, and it starts when you create the benchmark. Typically, models do very poorly, and then over time people iterate, and you can kind of track progress on the benchmark. And eventually, typically AI developers will kind of achieve saturation. So they'll model performance will it'll either reach 100% or there'll be some errors in the benchmark, and the model will kind of do as well as it can be reasonably expected to do, because we kind of think about there being like a noise ceiling on some benchmarks. But regardless, the point is that you start out, models do poorly, some time passes, people improve them, and then they get better. The benchmarks are tricky to, or it's difficult with normal benchmarks to track progress over a very long period of time, because benchmarks are typically kind of restricted to either some particular domain, or they kind of have the tasks in benchmarks have a somewhat similar level of difficulty, and so to try and understand how progress in AI happens over a span of like many years.
Yep.
I think, before this work, the kind of status quo was comparing different benchmarks to one another. So you're like, okay, it's 2017, and you have these like simple kind of problems for models, and we're like, okay, models can start doing those, and then now it's 2025, and we have these like way harder benchmarks, and we're like, we can see that there's been a lot of progress, but it's actually it's really hard. We don't actually have like a kind of a single metric to track this progress. We're kind of doing this qualitative comparison of the difficulty of benchmarks over time, and this is like messy, and people have different priors, and so this work was kind of motivated by trying to have a kind of a y-axis, basically, a way of tracking progress and seeing what the trends in AI progress have been over a longer period of time than individual benchmarks typically have. And so the way we do this, or the way we operationalize this, is we look at the length of tasks that models, the length of task for humans, that models are 50% likely or some percent likely to be able to succeed at.
Right.
So we have a really wide range of tasks, ranging from like a few seconds all the way up to like 8 or 10 hours. And then and crucially, this is the time the tasks take for people to complete. And we have a kind of combination of having a bunch of people attempt the tasks, and we see how long they take, as well as just kind of estimating how long the tasks take. And then for any individual model, we look at models do really well on the very short tasks, and then they do poorly on much more poorly on the long tasks. And we kind of look at for some given success likelihood, how long. How long can the task, or how long are those tasks? We kind of estimate this in a particular way that we could get into. But the main takeaway is we want to see, like, for different models, how long are the tasks they can complete. And what the kind of very striking thing that we found is that there's an extremely over the past roughly 5 years, there's been an extremely robust kind of systematic trend in the length of tasks that models are able to complete. This to our kind of best ability to understand the data that we're seeing, it seems like this is fit very well by an exponential function. So the length of tasks that models are able to complete has been increasing exponentially over this period. There are big questions over how well we can expect this to continue in the future, but yeah, it seems like there, over this period at least, with this data that we've collected, there's been this exponential trend, and yeah, that's I think the kind of striking result, and the kind of key novelty I think for us is this kind of unified metric that can be applied to different benchmarks. For example, for different benchmarks, you can measure how long do these tasks take people, right? For very simple, natural language processing kind of benchmarks, that were common in the 2010s. These tasks I think typically don't take people very long, like a few seconds. And then for a lot of the tasks that people are kind of having agents, complete now, like kind of difficult software engineering tasks. These tasks take people, somewhere in the range of, hours or something, and models can sometimes complete those. Although, they're still somewhat unreliable.
Gotcha. So, okay, first, before we go in, I guess I'd like to get a sense of what we're talking about. So you say that there's some tasks that take seconds, some tasks that take minutes, some tasks that take hours. Can you give me an example of what's a thing that takes seconds? What's a thing that takes minutes? What's a thing that takes hours?
Yeah, totally. So, one example for the kind of that's representative of the tasks that we created that take people a few seconds to complete. One example is given a few files on a computer. Which of these is likely to contain your password? And the file names are password, email, whatever.
I think it says credentials that text. The example in the paper, So it's a little bit, it's not quite so.
Right. Yeah.
So that's an easy one.
Yeah, that's an easy one, and we have kind of others that are similar.
And what's the first to give me a feel for how that relates to AI progress? What's the first model that succeeds at that easy task?
Yeah, that's a great question. So GPT-2 succeeds. GPT-2 is actually the first model we tested. Okay. So I actually don't know if earlier weaker models would succeed. I actually would bet that they would. I would bet that BERT is able to do this, for example. But we only went back to 2019.
Gotcha. And then to give me a feel for what it means for an AI to complete this task. So GPT-2, my understanding is that it's basically just text completion. My understanding is that in the release, it did not have tool use capabilities or stuff that modern LLMs have. So what are you actually doing to start with GPT-2 and end with does it succeed or fail on this task?
Yeah, there are different things you can do, I think, that are reasonable here. I can't remember the specific one we ended up on in the paper, but one example is just looking at the likelihood that the model puts on these options.
Sure.
So passing in the input, and then the question, and then seeing GPT-2 is a language model, and so it outputs likelihoods for tokens that are passed in, and you could just kind of compare the likelihoods and see. I think this would be a reasonable baseline.
Oh yeah, and I guess this is less of a computer use thing than a multiple choice thing, so it's easier to see how GPT-2 could do that one.
Yeah, exactly. So for GPT-2 kind of attempting much longer tasks, you can't use this kind of same methodology.
Sure. So speaking of longer tasks, so that was an example of a very easy task. Can you give me a feel for what an intermediate task might be?
Yeah, so some examples of intermediate tasks that come to mind are kind of simple software engineering tasks, or data analysis, or we have some kinds of kind of basic like reasoning questions. So one example that comes to mind is you're given a short kind of CSV file that just contains some data. It has like, I don't know, 50 or 100 rows of data, and you just have to write a very simple script that is like 20 or 30 lines of code
Mm.
to kind of parse this or process it in a certain way. And so this takes like someone an experienced data scientist maybe a few minutes. Maybe it takes someone more junior like 15, 30 minutes or something.
Yeah.
Yeah, that's I think a representative example of these kind of shorter like intermediate tasks.
Okay. And yeah, when you're measuring time horizon, like, different people take different amounts of time to do this. What counts as the time it takes humans to do it?
Yeah, so I think there are like there are different reasonable ways of doing this. The way that we approach this is we have one thing to say is, in general, we with the time horizon metric, we are kind of trying to get at something like uh, you know one thing you could do that I think would not give you very interesting time estimates
Mm.
is you could randomly sample a person in the world, kind of off the street or something to do each task.
Yep.
I think this like wouldn't be a very useful measure of how long these tasks take people, because in general, those people are not completing these tasks in the real world. And so the thing we're trying to get at with this metric is, we want it to be very intuitive. We want it to be kind of clear. If an AI system can do tasks of X length of 15, 30 minutes, an hour, 2 hours, how does that translate into the real world? We want that like connection to be very direct, and so we want to have people attempt these tasks that we would kind of naturally expect to be doing these tasks in the world. So we have, we kind of try and, have people who have roughly a kind of, reasonable amount of expertise in the different areas
Okay.
who we might expect to do them. So that's the kind of, that's the like expertise, like sampling question. Then there's like, we still have multiple people attempt
Yeah.
many of these tasks. Sometimes they succeed and sometimes they fail. And so there's this question of, well, do we include their failures? Do we just kind of use successful times? I think there's like reasonable discussion about this. One thing it would be nice to do is include their failures. But
Mm.
I think, because if we have someone who has a reasonable amount of expertise, but they fail at a task, I think that is information about the task, being kind of, more difficult.
Yep.
But I think you would need a larger number of people to attempt the tasks in order to actually kind of use that information effectively. You could do something kind of like survival analysis
Yeah.
from the medical industry, where that they failed after a certain amount of time, but it's possible that they would have succeeded, in the future. And so, anyways, but the thing we actually do in the paper is we use the geometric mean of the successful attempts. And we use the geometric mean because we think kind of completion time broadly is kind of distributed like logarithmically, or sometimes people will take much longer than other people, and we want that to we don't want that to like kind of totally dominate the time we're estimating for the tasks.
I wonder. I guess one question I have about that is, so suppose you're looking at tasks. You're looking at tasks, and you're looking at completion time for the kinds of people who are able to do that task.
Yeah.
I worry that might sort of compress the difficulty ranges. So like one intuition here is like, how much time does it take people to multiply like 67 and 34 by hand. Like the answer is like there's there's a pretty large range of people who are able to do that task,
Yeah.
and it probably takes them like a couple minutes. Um, then you can also ask, okay, how how much time does it take people to solve a separable differential equation, right? And well, if you're able to do that, it's actually like not that hard. It depends on the differential equation, right? Right, depends if
Yeah.
if it's a thing you can integrate easily. But it's like, um, probably for people who can succeed at that task, it takes about as much time as like it takes people who can succeed at the task, multiply these two-digit numbers to do that.
Yeah.
But like, it seems like there's some sense in which the solving the differential equation is harder, right? And maybe you want to say, oh, it's like the thing that's harder about it is background knowledge and like whatever, I don't know, things could just learn background knowledge and we kind of know that. But yeah, I'm wondering what do you think of that worry?
Yeah, I think this is like a fantastic question that like really like I think this gets at like a lot of what's going on here, what's like interesting about this work. Yeah, I should say that I think we're like we're getting into kind of more speculative territory or something.
Sure, sure.
Basically, I mean, yeah, there are a few things to say. So one is in terms of the kind of unique value of this approach that we're taking with this time horizon metric. There are a lot of benchmarks
Hmm.
that try and come up with kind of the most difficult for people questions, and then having AIs try and do them. This
Hmm.
is in fact I think the kind of standard methodology for saying like, oh yeah, this AI system is like smarter than another one, is that it can do problems that fewer and fewer people can do. So we started out with like common sense questions that like most people can do in the 2010s. In over time, over the past couple of years, models have been able to do. So yeah, I worked on this benchmark GPQA that uh, uh, had like very difficult science questions, kind of PhD level roughly. And models are able to do that now, and they yeah, GPQA I think is like mostly saturated or like pretty close to it. Models can do like IMO questions, right? International Math Olympiad questions
Hmm.
that like very few people can do. And so I think that's like I think this is a kind of important axis to like measure AI capabilities along. Like difficulty for people. But I think this misses a lot of what people can do that AI systems can't do.
Yep.
And one of the key things that we're trying to get at is you know how can we reconcile the fact that models can do these IMO questions, that they're like geniuses in some sense, but they're like kind of idiots still, right? You ask it to like book a flight for you, and maybe that example is maybe models can do that now, but
Hmm.
even like kind of slightly harder things, they kind of fall over often on. And so I think that's the thing we're trying to get at. And so we actually want to we want to kind of factor out the kind of like how much expertise do you need, and one intuition for I think kind of what we're trying to get at is something like the number of actions that are
Hmm.
required to complete this task. I think this is like a very difficult to operationalize, or like it's like very kind of problematic and mushy. But like one intuition at least is that this metric, if we factor out the difficulty of problems and we just look at how long they take people who have a reasonable amount of expertise, then
Hmm.
maybe we're getting closer to something like agency more broadly. And I don't want to overclaim, or like it's I think this is still very much an open kind of area, but for example, like number of actions, I think is also a very reasonable thing that I would expect to be kind of correlated, although I think it's probably more difficult to estimate.
Fair enough. Um, so okay. Uh, Getting us out of that rabbit hole for a little bit. So yeah, an intermediate level task that might take like I don't know 3 to 15 minutes for a relevant expert is
Yeah.
like take some CSV file or something and parse it.
Yeah.
And yeah, to help us get a sense for that. At what point do language models start being able to succeed at this sort of task?
Yeah, language models start being able to succeed. I might get the exact years slightly wrong, but somewhere in the range of like 2022-ish is I think where models are able to do this. Actually, maybe back casting from the trend from where we are now. So yeah, the specific like trend that we found was that there's been a 7-month doubling time over the past five-ish 6 years.
Hmm.
Currently, models are able to do tasks with like 50% or yeah, we estimate 50% success likelihood of tasks that are like about 2 hours long. So
And currently is late September 2025.
yes,
It may take me a while to edit this episode and get it out, but that's what we
yeah.
mean by currently.
Yes.
Um,
Thanks. Yeah, and so if we go back, so 2 hours to 1 hour is like early this year. Another 7 months to 30 minutes is yeah, like spring 2024, and then maybe yeah, 15 minutes is like middle of 2023 or something. That might be I think that should be right. Yeah.
okay.
Um yeah, so yeah, actually yeah, a bit later than 2022. But yeah. Um yeah, and so that is yeah, what models are coming out around then. Um yeah, wait, actually what models are those?
Oh, I don't know. I hope you might know. Um,
Yeah, so let's see. What is the exact timeline here? Something like
is GPT-4 2023-ish?
yeah, right. GPT-4 is January, or yeah, is like beginning of 2023 or
Mm,
like end of 2022, one of those.
okay.
Yeah, so I think it's like yeah, roughly GPT-4 ish.
Okay.
Yeah, and that kind of lines up I think with my intuition here.
Okay. So we've got an example of an easy task, an example of an intermediate task. Can you give me an example of like a hard task?
Yeah. So the hardest tasks we have are, take people yeah, something yeah, like 6, 7, 10 hours to complete. These are yeah, so one of the kind of sets of tasks that we use actually are this yeah, come from this benchmark that we released about a year ago, or close to a year ago, called RE Bench,
Mm,
which stands for Research Engineering Bench. So this is a set of kind of yeah, challenging ML research engineering tasks. So yeah, one example is you're given a neural network whose embeddings are permuted in kind of a way that don't know. They're kind of scrambled, and yeah, your task is to yeah, fix the embeddings basically
mm,
of this model. And yeah, you can kind of do like fine tuning or data analysis to try and understand like what's how they were scrambled, and see if you can like reconstruct them. And so it kind of yeah, requires some like intuitions about how neural networks work and how to fine tune or work with models at a relatively low level. Yeah, they're kind of a range of other tasks. But yeah, these tasks take yeah, kind of ML engineers roughly like 8 hours to do kind of decently well on. And so yeah, I think that's like one class of tasks. I mean, yeah, we have other kinds of software engineering tasks, for example, or like cybersecurity tasks that take quite a bit of time. Uh, uh, yeah, so one example, yeah, that comes to mind. I think we didn't actually get a a baseline on this.
mm.
I think this task we're just estimating how long it takes, but um, there is yeah, the this task has a modified implementation of a kind of older standard uh, um, hashing algorithm, MD5, and the task is to find a hash collision on this like modified version of this older hashing algorithm.
Hmm.
There are standard attacks that that kind of work on this algorithm, or like there's kind of literature on attacks. It's not impervious, but you have to kind of like know which are the right ones. You have to understand the algorithm pretty well, and then you have to be able to like modify the attacks, or like figure out
Right.
how to change it. So this one is a little bit more like expertise heavy, maybe, than kind of like serial action heavy.
Sure.
But and so there's a bit of range there, but yeah.
Okay. So one thing that strikes me about the tasks that you mentioned
Mm.
is that they all seem very related to computer programming, and especially sort of like programming, data analysis, machine learning, like cybersecurity things. I believe that that this draws from work from this benchmark that I believe you were the lead author on, human calibrated autonomy software tasks, or HCOS for short. Which my understanding is that those are the 5 areas that covers.
Yeah, broadly, yeah.
Yep. Yeah. Why the focus on software engineering type things?
Yeah, great question. So I think there are at least a few reasons.
Hmm.
So one reason is that some of the kind of threat models that Meter is most concerned about are like very kind of contingent on AI capabilities in some of these particular domains,
Hmm.
like software engineering, cybersecurity, and like AI R&D in particular. Um, and so we're kind of most interested in measurements of AI capabilities in these domains because we think that these are kind of highly relevant for estimating risk, in particular
Hmm.
catastrophic risk from AI systems. And yeah, happy to talk about those threat models. Um, uh, that's kind of one reason is they're just directly relevant.
Hmm.
Another reason is uh, there has been there's been a lot more like focus, I think, from AI developers in these domains,
Hmm.
and so um, we're kind of measuring something that's like closer to what they're focused on. And I think this has some trade-offs. So one trade-off is or like one objection to this is like, but they're AI systems are really bad at other stuff because developers aren't focused on it.
Yep.
And so now you're like overestimating their capabilities. And I think that's basically like a legitimate concern, or I think that is true. Uh, but I think there's this question of like kind of um, if the methods that AI developers are applying to improve models in these particular domains are general enough and are kind of working well in these domains, and they're general, then
Hmm.
we might expect it to be kind of relatively easy, or kind of more a product of just kind of general like commercialization to apply these methods now to like a broader range of tasks.
Hmm.
And so I think there's kind of this idea that we're like or I think we want to like aim for some balance of these, and we want to understand like how much generalization there can be from these domains, and there are like kind of open questions around this, but um yeah, I think that's another reason. And then finally, it's just easier to measure AI capabilities in these domains. We're software engineers,
Right.
and in particular, one of the kind of big things is if you want to have a benchmark that is kind of easy to run and easy to evaluate a model's performance on. It's much easier to do this in domains where you can kind of more formally like verify model outputs. So if you want to understand how well models can like summarize text or like write creative fiction or something,
Hmm.
it's really hard to write some code or automatically verify that this creative fiction is like actually good. Like you would, yeah, there are ways of kind of getting around this, but to some extent, but yeah.
Yeah. I guess one thing that occurs to me, that I don't know if Meter is like best positioned to do this, but a thing that I kind of wish happened more is just like ecological understandings of just like do ecological in a loose sense of like, do people use these things, right? Like, do people successfully, like when AI writes fiction online, like how many
Yeah.
downloads does it get? Like, does, how often do people choose like AI therapy over human therapy, or like whatever?
Yeah.
Like it feels, I don't know. I guess my wish for the world is that we had like better ways of tracking this sort of thing. But it does
Yeah.
feel like one way you could like it does rely on people accurately being able to assess how much AIs are like actually helping them in these domains by
Yeah.
their use patterns, which I guess another meter work about uh measuring like open source software developers, seeing like if they were good at estimating how much AI helped them. Like the answer was they were bad at estimating them.
Yeah.
So maybe like people are using AI all over the place, and it's not actually helping them. But like it does seem like one way of addressing some of these concerns.
Yeah, yeah, totally. That seems pretty. I'm super interested in this sort of thing. Yeah, there was recently the Anthropic Societal Impacts team. I
Mm,
think didn't quite get as far to the kind of measuring like number of downloads or something, but
yeah.
in terms of like kind of yeah, they did some work recently. I haven't looked at it closely, but yeah, like kind of breaking down into like really fine grained categories, like what Claude usage looks
Oh
like,
yeah,
which
yeah.
I think does to some extent, or like I think you probably like these probably would be pretty correlated or something. Like if there's a strong like market demand for a certain kind of AI output, I think you would expect to see that show up in your like Claude usage data to some extent at least.
Right, right.
Yeah.
Yeah, fair enough. Um, cool. So okay, so we were talking about why software engineering. The answer is like there are three parts of the answer. Firstly, it's related to some threat models that Meter cares about. It's also like easier for to measure. Wait, I think there was a third thing in between those that I forgot.
Yeah, yeah. The third one is like I think this is kind of the sketchiest of
Hmm.
these. I think those are the two. Those are probably the two biggest ones.
Yep.
The third one is something about like AI developers are
Oh
kind
yeah,
of
they're
pushing.
aiming for.
They're aiming for this.
Yep.
And this has like yeah this kind of trade off that I talked about
Yep.
in terms of generalization. But yeah.
Got it. So I think the next thing that I want to talk about is there's like one interesting thing about what you're doing, right? Is you're basically saying like, okay, we want to know how AI succeeds at tasks of various difficulties,
Hmm.
and you could imagine like if I'd never seen this paper, right? I could imagine having like a whole bunch of measures of difficulty, right? Like
Yeah.
I could use like a human rating of like on a on a scale of 1 to 10, how hard is this? Or
Hmm.
like how many years of education do you need for this? Or like when people try it, what's the probability that they succeed? Um, or like if there's some competition between AI agents or whatever, you can look at the elo of it.
Yeah.
That only works in some domains, but like Go is a really good one for that, for example. And one that you do in fact look at in the paper is like kind of the intuitive messiness of a task, like how
Yeah.
clean and simple is it versus like how you know tricky, rough is it.
Hmm.
Um, and the thing you end up finding is this really nice relationship with time it takes for humans to do it, right? Where it seems like both you have a decently good relationship where like like within a model, right? Where like things that take longer to take longer for humans to do, like success rate at these tasks is lower.
Hmm.
And also like across time, there's this like nice trend for this.
Yeah.
I'm wondering like, is this just like the first thing that you tried and it seemed like it worked well, or do you have a really good sense of like, no, we checked, and these these other metrics just don't have as good relationships in a way that's nice and predictive.
Yeah, yeah. So we've definitely done some of this. I think we probably we like I think there's like a vision of like we've tried all of the things and this is like the
Right.
one. And like yeah we definitely haven't done that.
Yep.
Yeah, maybe it'd be useful in particular yeah to talk about like the specific kind of alternatives or,
Mm.
or or something. Um Yeah, I mean, I think for at least a couple of them, like maybe the first two I think you mentioned, how difficult do people rate these tasks, or like when people attempt the task, what is the probability of them succeeding?
Yep.
I think both of these are kind of closer to the kind of standard benchmarking like paradigm,
Mm.
and so I think yeah, those metrics I would expect to correlate more or be more connected to this like intuitive notion people have about how much expertise does a task require,
Mm.
which I think is kind of already kind of covered by other benchmarks. That's not to say though, I guess, that we couldn't still use it as this metric, or maybe we would see a robust trend. But I think it'd be yeah, that's interesting. I think it'd be kind of difficult to like operationalize these in a way that like makes sense. So for success probability, like what is the exact actual distribution of people that you are having attempt these tasks, right?
Mm.
That becomes very load bearing, right?
I
Because
mean, it seems like it's similarly load bearing for success probability as for time horizon, right?
I'm not so sure. I think that so one of the reasons why we filter our baselines to
Yep.
only ones that succeed is success on a task is in fact a lot more information than failure on a task. There are
Mm.
like a bunch of reasons why you might fail a task
Mm.
that don't really that aren't like kind of actually a lot of information about how difficult or like this kind
Mm.
of like how much agency is required or whatever. So for example, I mean, maybe we just got their expertise wrong. Like the person, we're like doing this job of like kind of manually assigning people to tasks that we think are relevant for, or yeah, that they have like a lot of relevant expertise for, and like
Mm.
maybe someone just like happened to not ever use this like particular tool or set of tools that are like super important for this task, and then their failure on that task is like, it's still some information, but if they succeed on the task, then that is just like this very objective thing. Like, yes, someone can complete this task in this amount of time. Other things, there are like infrastructure reasons why people fail tasks. Also, there are like incentive reasons. So when you have people try and complete tasks, sometimes they'll get bored, and they'll want to stop. Sometimes they'll be like, this is too hard. I don't want to keep doing this. Sometimes people, incentives can be kind of tricky to set up
Mm.
well in different cases. So like one situation you can have is where people quit tasks early because they want to like maximize the chances of getting like more tasks that they succeed on. Typically we like
Mm.
pay bonuses for success because we want to incentivize people to succeed. But yeah, that can lead there's kind of a perverse incentive there. And so broadly, we just have like a lot more uncertainty about failures, I think, than we do about successes. That's not to say I think that we couldn't do something like this, but or like it's I definitely can't say it's impossible. But I think it's more challenging.
Okay.
That's like one. I don't know. This is like one particular thing. I think they're like there's I'm probably not getting at the like broader or like
Yeah, or maybe one thing. Yeah, maybe like one way to get at the same question is, so you find this pretty good relationship between like task completion, like time to complete task among humans who are relevant experts who in fact manage to complete the task, and a like AI probability at succeeding at the task, and B, like trends over time in time horizons that like models can do at a 50 or 80% success rate, right?
yeah.
But like it's not perfect. And one thing that
Mhm.
one thing you mentioned in the paper that for some reason it seems to have like gotten less mimetic,
Hmm.
but like people seem to talk about it less, is yeah, you have this like metrics of messiness of
Yeah.
various tasks, right? And you end up saying like, okay, there is something to this messiness thing that like somehow seems to predict task success over and beyond human
Yeah.
time horizon,
Yeah.
right? So like, I mean, one question to ask is like, okay, if I had to choose between just human time horizon and just these messiness ratings,
Hmm.
which one would do better? And maybe the next question is, okay, like if both of them are independently predictive, what does that say about like the ultimate metric we really should be using?
Yeah. Yeah, so I'm super I think we are broadly like really interested in trying to explain as much of, the variance in models, successes and failures as we can. And you're totally right that the length of task for humans is one metric that explains like a decent amount of this variance. But there are definitely other things that are going on. So definitely yeah, like I think that we're like actually kind of currently trying to figure out like what are other properties of tasks that explain their success and failure well. And I think we would love to have something like this. I mean, for something like messiness, like I think there still is or yeah, for a lot of these other kinds of metrics that you can think of,
Mm,
to me the biggest issue that I see, or the biggest challenge, is just some kind of thing of subjectivity.
yep.
So people have like very different senses of like what is a messy versus clean task,
Mm,
and kind of depending on your like priors about uh, you know so yeah, one example is I have a colleague who I think it's fine. I think it's fine for me to talk about this.
mm,
Like he basically like would not rate any of our tasks as being messy at all.
mm,
Because they have algorithmic scoring functions, for example. So the success or failure is like defined by this like kind of like small surface area or something. Um, and they tell you the tasks like tell you what to do, for example, right? In the real world,
right.
like a lot of the challenge is figuring out what the hell you should do in the first place. So I think that's like a challenge, but I definitely think, I mean, especially with you kind of mentioned this randomized control trial that we ran recently of developer productivity, where we saw that um uh, developers, at least when we measured this, were not sped up by AI systems. And trying to understand like what the gap between benchmark scores and this some of these more ecologically valid experiments, what that gap is or what explains that gap. I think we're like super interested in.
So actually, speaking of the relationship between how good things are at predicting success. So
Hmm.
one thing that you also do is you look at the variance or the correlation between models of like, if model A succeeds at a
Yeah.
task, like how does that predict whether model B succeeds at the task as
Hmm.
well? So this is one of these like fun diagrams that you have in the appendices, and it's possible that you just don't know the answer to this question. But one thing I noticed when looking at these diagrams of correlations is there's this block of like GPT-4 and beyond models that
Yeah.
seem much more correlated with each other on what tasks they can succeed and fail on than pre-GPT-4 models. What's going on there? Is it that they've like standardized on training sets? Is it they've like are they now like is everyone after GPT-4 like trying to train their models to do software engineering and that's what's going on? Or yeah, tell
Yeah.
me about that if you can.
I don't think actually know the answer to this. I can speculate. Um, I think I'm not certain that this isn't like an artifact of our kind of particular setup. So one thing you brought up is GPT-2 uh has if you put GPT-2 in the same kind of agent scaffold. So for
Mm,
recent models, we have them in this loop where they see some instructions and some the state of their environment, and then they think about and consider what actions to take, and then they take an action and use some tools, and kind of continue. If you put GPT-2 in this loop, it just like totally flops.
mm,
And so it's basically like you kind of you can't really make like a perfectly direct comparison, or like you do actually have to use like a different methodology. I'm not certain that yeah, this like kind of block in the correlations isn't because of some difference in like our agent scaffolding, for example. Um, yeah, yeah, it's a really good question. I would be curious to know. Yeah, I actually don't know if we know. I feel like I yeah.
Yeah.
There's probably been some discussion about it, but yeah, I need to check.
Oh, also another thing that it just occurred to me with
Hmm.
the alternative difficulty measures. I have a colleague. So I have a colleague of mine back when I was at Chai called Cassidy Laidlaw who has a paper. I forget what the name of the paper is. It's going to be in the description, and I'll send it to you afterwards. Where basically the thesis is, if you want to know whether deep reinforcement learning works on an environment or not, um, like if you're familiar with reinforcement learning algorithms, or like one one idealized reinforcement learning algorithm you can do, you can start off with a random policy, and then you can do like iteration where like, okay, what would be the best action for me to take given that like from this point onwards I'm just going to act randomly, and then like, okay,
Hmm.
what would be the best action for me to take given that from this point onwards I'm going to do the thing that would be best given that from that point onwards I would act randomly,
Hmm.
etc.
Hmm.
And I think like basically a prediction of like a very good predictor of how well deep reinforcement learning works on various environments is just like how many steps of that do you actually have to do?
Hmm.
If I recall this paper correctly, people can read it
Yeah.
in the appendices, and
Interesting.
I feel like something like that might be, well, like one nice thing about this is that it sort of gets to, it doesn't get to the access to the aspects of messiness that are like vagueness or whatever,
Hmm.
because like this is just reinforcement learning where you have a defined reward function, but it does get to some of the like agenty, how much do things depend on things
Yeah,
thing.
yeah, totally. Like kind of how fragile, like, yeah, yeah, interesting.
Yeah, embarrassingly, I remember very, very little about this paper, but it's people should read it. Um, so I think the last thing I want to ask about, in the well, like kind of digging deep into the time horizon stuff, is that at least for now, one thing that readers notice when looking at this is there's basically this line on a log plot of like, year and time horizon, and like models are basically like lining up along this line, but then it starts looking like once you get reasoning models they start like bending up a little bit. They're a little bit above the line, right? um and as of the AI ability to complete long tasks, I believe that was released in like February or March of this year.
Yeah,
So,
March.
like
Yeah,
pretty like early when we had not as many data points. We've
yeah,
gotten a few more data points.
yeah.
And yeah, early on there was some speculation of like, okay, have we like, are we going super exponential or not?
Hmm.
Um, with more hindsight, are we going super exponential?
Yeah, great question. I would love to know the answer to that. I think we still like don't really know.
Hmm.
I guess yeah, a couple things to say at least. So one is yeah, yeah, since we released the paper in March, new oh yeah, one thing that'd be useful to just point out
Hmm.
for listeners is that this plot where we measure the trend of improvement over time, we're only using the best kind of model at a given time.
Yeah.
And so that's just relevant because yeah, there are a lot of other models that have different have different like trade-offs, or like maybe they have faster inference but they're weaker, and we're just using the models that perform the best.
Hmm.
Um, anyways, since March, yeah, frontier models. So one thing we kind of look at in the paper is we yeah, we kind of noticed, or actually yeah, this is useful to talk about because I think the timeline is like useful for understanding, like, or the timeline of how the paper came together is useful. So we actually initially only fit the trend on models from I think basically 2024 onwards.
Hmm.
So yeah, I think the first version of the graph was made by Ben Weston in December 2024, if my memory is right. And yeah, I think this was just using that year's models.
Hmm.
And with those models, we actually observe, yeah, like this 4 month kind of doubling time
Hmm.
in the time horizon. And then we were like, well, does this trend extend backwards? And so we kind of do in the paper we also do these kind of backcasts
Yep.
from this, but so then we kind of added in previous models. All that's to say that we to some extent from the start we kind of have seen these like two trends essentially. I mean, I think this is all kind of uh like I don't know, BS or something like
Mm.
once you start if you have like 10 data points or 15 data points and you're like fitting like piecewise linear functions, like it's kind of it's like pretty sketchy. So I don't I like definitely don't want to overclaim, but like um it it does seem like this like 4-month doubling time trend from 2024 onwards has continued to hold, or has been like a much better predictor than this like 7-month doubling time that is suggested by the models going back to 2019. So I think like my like best guess that's like very low confidence is something like we're kind of just on this like 4-month trend now, but it's still kind of just exponential, or it is really hard to like distinguish between like different kinds of model fits to some extent.
So, and yeah, actually, the things that, about like different models
Mm.
made me wonder. So if we're saying that like time horizon is going up over time, that means just suppose I want to project that into the future, right? It's one thing if this is true at like basically fixed cost, right? It's another thing if
Yeah.
like, like it's always the case that, a 1 minute task costs $1, a 2 minute task costs $2, a 4 minute task costs $4, and then like
Yeah.
you know, like maybe we get taught models that can technically do things, you know, like that a human could do in a month, but like it would be cheaper to just get the human to do it for a
Yeah.
month. Off the top of your head, do you happen to know like what the picture looks like with cost?
Yeah, that's a great question. This is something we try and keep an eye on. So um, I don't. Yeah. Let's see. So for recent models, we have been using like our agent scaffold has a token limit that we tell models about, so
Mm,
that they're aware of this. But I think we've been using a token limit of something like 8 million tokens,
mm.
which I think for these longer tasks ends up being like at least one order of magnitude cheaper than paying a human with relevant expertise to complete the task.
Right. And
Um,
to give a feel for that, 8 million tokens is something like 6 Bibles of text,
um,
roughly.
it's quite a lot. There are questions or like you can do much better than that with like caching. So
Mm,
yeah, like most APIs let you like do like prefix caching, and that helps quite a bit. And so
okay.
or you should count it kind of differently, I think. But
But it's like a big chunk,
it's a big
basically.
chunk. It's a big chunk. Yeah, models will do lots of reasoning and run a bunch of different experiments on these longer tasks. Um, uh, yeah. They'll take something like uh 10 to 50 actions or something kind of in the environment. But then, for each action, they're like doing a bunch of reasoning, and
Right.
often they're, it depends on the exact agent scaffold, but in many of them, we have like models that kind of propose actions and then review them and then select the best one. And so there's kind of a lot going on, and this is still much cheaper than having people do it. I wish I knew the exact numbers on cost. It is more complicated because of caching, but so currently this isn't like the biggest concern of ours,
Mm,
because of this, basically, where you know basically, models still are just like highly cost competitive. I totally imagine this changing at some point. Um, just trends in models kind of being able to use test time compute more effectively. I totally expect for very long tasks this to get expensive, and it to be like very very important to be measuring the kind of Pareto frontier of cost and success rate or something. And I think we're excited to do work on this as it becomes more relevant, I guess.
Yeah, fair enough. So like zooming out, METR, so model evaluation and threat research. I kind of think of METR as like trying to figure out how scary models are. And if they're scary enough, then like, I don't know, maybe we should do something. So this kind of work of measuring just sort of general software engineering capabilities, right? And trying to forecast them over time.
Yeah.
What's the rationale behind this? Why focus on this?
Yeah. So I think there are broadly the kind of threat model that METR is kind of most concerned about, at least at the moment, is kind of rapid acceleration in AI capabilities, and in fact, like the rate of progress of AI capabilities due to AI systems being able to contribute substantially, or like contribute the majority of AI progress at some point in the future. So yeah, the idea is currently, the way you make AI systems better is through a combination of, compute, hardware resources, money, data, and talent, labor, right?
Mm.
If it becomes the case that AI systems can kind of replace the labor, the talent part of this, in kind of economic models of progress, in at least some of them, I think broadly like they're reasonable, although I'm not an economist. So
Mm.
you can see very very rapid progress, and basically this just seems like broadly kind of scary or something. So one example is you might see like very rapid centralization of power in a single organization that does this kind of recursive self-improvement, and that's concerning, for kind of general like stability, geopolitical, like democracy kind of reasons. And then you also your kind of arguments for why the AI system itself is not going to kind of be dangerous.
Mm.
Those might break down. So you might not be able to evaluate it effectively because, for example, the system, may have like a really good understanding of exactly how you're evaluating it, and if its goals are different from yours, then it might be very easy for it to game your evaluations. Your kind of supervision methods might break down. You're reading its chains of thought, for example, and it looks, the model is saying things that seem very safe and nice and reasonable, but actually it's doing some kind of hidden reasoning in the background that you can't detect, and you didn't realize that this was about to happen because progress was so fast, and because as a lab you were just like scrambling to kind of get as much compute and make as much progress as you can, as quickly as you can. And so yeah, broadly, this is, I think, one of the kind of big concerns, or questions that we want to understand is how close are we to this kind of rapid acceleration? Is that even possible? I as I said, like, labor is not the only input to AI progress. You also have, compute, for example, and data, and those things, these things might be kind of highly complementary to labor, such that even if the amount of talent increases by several orders of magnitude because you have all your AI researchers doing this work, you still might you might end up still very bottlenecked by compute and data. And so trying to get some understanding of that, I think like we're like we do some work, or we think about this to like some extent, these kind of like economic models. I think this like isn't our like chief kind of forte or something. Epoch AI has a bunch of great work, kind of doing some of this modeling. Also, yeah, folks at I think the org is called Forethought.
Yep.
Will McCaskill and Tom Davidson have done work on this kind of economic modeling. Anyways, yeah. So understanding how capable AI systems are is a big input to this, and yeah, software engineering and ML research capabilities are kind of highly relevant.
And how much is the desire to? So one thing you could do with this is you could say like, okay, like, are we there or are we about to be there? And like that's the point of doing the measurements. Another thing you could do is you could be trying to say, okay, are we going to get there in 2030 or are we going to get there in 2050 based on what we know now? So yeah, how much is the thing you're trying to do like a forecast versus a now cost?
Yeah, that's a great question. I think we would love to be able to do like really good forecasts. Uh, Unfortunately, I think it's really hard.
Yep.
So yeah, for example, as we kind of talked a little bit about, new paradigms in AI might change the trends that we observe. Also, there are lots of inputs to these trends that might not be durable. So for example, like we're seeing like the time horizon of AI systems is increasing exponentially, but also the amount of money that and the amount of compute being put into training AI systems maybe has also been increasing exponentially. I actually don't know the exact details of like how compute spend has been increasing, but
I think it's exponential.
Okay,
I feel like if I go to Epoch AI, they're going to show me some like nice graph. And it's going to be like, yeah.
And so maybe that's just the cause, and in fact, like we're just going to hit some like bigger kind of bottlenecks in the economy more broadly. Like it's just not going to be possible to like fund increasingly large data centers, and so there are a bunch of, I don't know, like I think this is kind of an interesting point. Is I basically view this like time horizon trend that we're seeing as something closer to like an economic model than like a kind of like ML like benchmark model or something, where I'm like the actual inputs to this progress are firms that are competing to train increasingly better models, and they're putting these resources in, and they have these constraints and whatever, and like I don't know, I think this was actually, for me at least, the one of the big updates or something is I'm like I guess I think I'm much more interested in economics as a result of seeing this like really robust trend, because so I was actually extremely skeptical of like putting time on the x-axis in particular.
Right.
I was like yeah, the inputs are just going to be these like random kind of decisions by different labs, like and there's no way we're going to see some like robust trend, because it just depends on who Jensen happens to like or whatever.
Yep. Jensen Huang being the CEO of NVIDIA, right?
Yeah. For different compute deals or something, and I was like, no way that could be like robust or something. And so yeah, that was a decent update for me. Like, well, maybe maybe these kinds of like extremely abstract economic models actually can be very very informative, or like maybe there is like this kind of deeper like systematicity to AI progress, even though, zoomed in, it feels very contingent and kind of arbitrary or something. I don't know. This is all like very much speculation, or like, just kind of my musings on this. I think as an org, yeah, we're definitely interested in forecasting. I think there are like, kind of trade-offs, between doing this like, more abstract modeling and just focusing on like, we do a lot of work on this like nowcasting kind of thing, like just like, currently how good are AI systems is kind of an open question, or like, there is a lot of disagreement about this. Even internally at METR, we have disagreement about this. Probably there isn't like one single answer, right? Because it's just a complicated question, but I think we're like trying to do kind of both to some extent.
Fair enough. So for either forecasting or nowcasting, right? Suppose I want to use the time horizons work or like the nearest successor to tell me, when are we going to get this like AI's you know, feeding into AI progress. How like how am I going to use the results of like, oh, it's like 3 months? Is that are we at recursive takeoff?
Yeah, I think this is kind of an open question, or like I
Mm,
don't think we have nearly as good of an answer here yet as we want. I mean, um we have like kind of heuristics. I think like one week of work, like time horizons of like 40 hours. I think we definitely are like getting a lot more kind of concerned, or it seems at least plausible that you could kind of successfully or like efficiently delegate like weeks worth of work to AI systems, and that you know I could totally imagine that speeding up AI progress quite a bit. Um, uh, yeah. Same for kind of time horizons that are much longer, but I think we don't really know. Is kind of my answer. I mean, part of this, I think, um, uh, or like part of my uncertainty. I think I probably would have been more confident in something like a week or a few weeks of work as like a time horizon that is very useful
mm,
for as some kind of like rough heuristic or threshold. I think I would have been more confident in that maybe um before this productivity RCT, where we found that people were very miscalibrated on how much AI systems sped them up, software open source software developers in particular, and in fact we saw that they were like slowed down on average by like 20%. Um, I think these probably, yeah, the time horizons work, and this randomized controlled trial results. I think they're probably not as like in conflict as they might like seem at face value,
mm.
for reasons that we could talk about, but um they definitely did update me more towards like kind of broader uncertainty about this like interaction between AI systems and people, and like maybe we do end up really bottlenecked by things like our ability to like specify tasks really clearly, or maybe things like kind of the fact that we're algorithmically scoring models. We might be like overestimating their capabilities because of that to some extent.
Yeah. Actually, in terms of other bottlenecks, I'm really interested in talking about that because
Mm-mm.
so if we're interested in like suppose I want to know like at what point do we get this like runaway process or whatever.
Mm-hmm.
Um it really matters whether AI is automating like, well, like suppose there are like 5 things you need to be good at to like to do
Yeah.
recursive self-improvement, right?
Yeah.
Like the difference between AI being able to do 4 of those and AI being able to do 5 of those is like huge,
Yeah.
right?
Yeah.
Yeah, I think one concern I might have about the meter benchmark stuff, or about this particular paper, is just yeah, is it covering all the bases or is it covering like some of the bases, like kind of, um,
Yeah.
and just because like potentially that could like really reduce its value for this particular um thing. I'm wondering, yeah, what do you have thoughts about that?
Um, I think that's a pretty legit concern. Yeah, I mean, I guess I would be interested in like or you know, there's this question of like, yeah, well, what are the kind of specific things that are bottlenecking, and kind of how different are they from the things that we're measuring? So one kind of broad reply could be something like, well, to the extent that our benchmark is just like a bunch of like kind of different diverse tasks, hopefully hopefully it's the case that we're kind of covering some decent amount of the space of necessary skills or capabilities, such that we would expect results to be like very correlated on things that we're not measuring specifically.
Mm,
And we can maybe get some kind of sense of this with by looking at the variance of model performance, like on our tasks.
right.
um
I
yeah.
guess one thing you could presumably do is just like have a held out 20% set and just see like, okay, does performance on like the held out set like, or does performance on the non-held out set predict performance on the held out set? And
Yeah.
I guess that's probably in some appendix somewhere.
I think the thing you would want to be doing there is you would want the held out set to be kind of importantly different in some kind of biased or like systematic way.
Yeah, yeah.
And I think that would be interesting. I don't. Yeah. Currently, we haven't done this. I mean, to some extent, maybe I think the kind of messiness analysis is kind of trying to get at something like this. Like,
Yeah.
are there other factors that explain model capabilities? It seems like kind of.
Yeah, I guess there's also this I guess it was a blog post Meter put out basically trying to do a similar analysis for other domains. So like,
Yeah.
there's a little curve for self-driving and there's curves for I forget exactly what all the other tasks were, but
Mhm.
so my recollection of that is that it seemed like in each domain you maybe had some sort of exponential increase in time horizons, but like best fit doubling times were different in different domains.
Yeah, I think so. So yeah, my broad takeaway from this work that Thomas Qua led was that in kind of uh you know decently similar domains, so like question answering benchmarks,
Hmm.
for example, so GPQA was like one of the benchmarks, and there were a few others. I think we saw like quite similar doubling times overall is my memory. um and actually even like overall pretty similar like absolute time horizons,
Hmm.
which was some kind of some amount of validation. The challenge with this kind of work is we put a lot of time into like estimating the lengths of our tasks, right?
Yep.
And so we're using these kind of like scrappier kind of more heuristic or less precise estimates of task length for most of these other domains. Yeah, and then I think self-driving did have a slower doubling time, but I don't think it was like clearly not exponential.
Hmm.
And then the other interesting takeaway I had from that was with respect to kind of like more general computer use. There are these benchmarks. There's this benchmark OS world that has a bunch of kind of like you have a browser and you need to do these tasks, or you're in this kind of operating system, and you have to click around and manipulate kind of normal software,
Hmm.
which is like a bit which is the key difference I think between this and a lot of our tasks is that our tasks are almost entirely kind of text only.
Yep.
Models are weaker relatively at multimodal tasks, it seems. But yeah, so I think for those domains, I think they had like something like a kind of similar doubling time, but the absolute time horizons were much lower. Like they were
Hmm.
like I think it was like a couple minutes or something, which I thought was interesting, and I'm actually kind of confused about broadly, or I don't really understand what's going on there.
So okay, with all that said about like kind of the pros and cons of this sort of framework for measuring kind of for tracking, like, are we getting close to some sort of self-improvement cycle?
Hmm.
I'm wondering, like, what's your guess about whether, let's say, 1 or 2 years from now, we're still thinking that like something basically like time horizon is the metric that we're tracking, or we end up saying like, oh, we actually have to, there's something like pretty different, and that's like the real thing.
Yeah, that's a great question. Um, yeah, I think to me, a lot of this comes down to the kind of tractability of continuing to kind of use this metric and like estimate it. So I think this is kind of this is somewhat unclear. So for example, you know, we we've paid a lot of people money for their time to kind of work on these tasks, and so we can estimate how long they take.
Hmm.
If the length of these tasks becomes like they're weeks or months long tasks, this gets like pretty
Right, right.
expensive.
Actually, how expensive was it to make this paper?
That's a great question. I think it's kind of tricky because there were like these different efforts going on. So like,
Hmm.
we included the RE bench tasks and the baselines for these tasks. And that was like kind of a separate project. So it's maybe
Yeah, yeah.
depends on if you count that. I mean, I think that the baselines for the kind of main set of tasks that we used, the HCAST tasks,
Hmm.
I want to say that these were somewhere in the range total of like at least tens of thousands, possibly low hundreds of thousands of dollars, something in that range.
Sure.
Yeah, I actually should I probably should know this
Fair enough.
off the top of my head more accurately, but yeah.
Yeah, but it sounds like it's reaching a stage where like measuring these time horizons is like getting close to the dominant cost of actually like doing this work.
Yeah.
There's still it's probably lower than the salary cost of you've got a bunch of people working on it, but like
Yeah,
if it were
yeah.
to become more of a thing.
At some point, I think, yeah, you this does start to dominate. Although, yeah, I would say that I think currently, like actually creating the tasks is the kind of most expensive and difficult part.
Mm,
Yeah, so either kind of creating them from scratch or kind of trying to like find good tasks in the wild, as it were, like which is nice because they already exist, and to some extent, although you have to kind of port them over into your framework.
yep.
But also, that gives you kind of more confidence that they're realistic and representative of real work that people are doing, which is important when we kind of don't fully understand exactly, when and why systems succeed or fail.
Mm.
Um, yeah.
Actually, yeah, maybe this is worth talking about a bit.
Hmm.
Yeah, I think there's one kind of approach to measuring AI systems, which says, look, we need to like isolate things. We need to get down to the like,
Yeah.
the simplest feasible task where we can really measure exactly what's going into it. And these end up being things, maybe like if you think of Arc AGI,
Hmm.
it's not quite this, but it's something sort of like this.
Yeah.
Um, versus a sense of like, no, we need to create things that are similar that have this like realness flavor, even if
Hmm.
they're not exact. Like, finding an MD5 hash collision, it's not like on some micro level, it's like not very similar to doing AI
Hmm.
research, right?
Yeah.
Yeah. Could you say a bit about like, yeah, the like how important it is to be thinking about like economic usefulness versus like trying to mimic a sense of like what the tasks you care about are?
Yeah. I think that there is a very real trade-off here,
Hmm.
between the kind of, yeah, level of like granularity of your like understanding, where if you kind of maximize that, you end up with, yeah, these like very kind of often like simple kind of formulaic, like systematic benchmarks, that are just probing some like very particular kind of skill, in a systematic way. Um, uh, and then on the other end, yeah, you have this kind of like realism maximization lens. So I think the best, like, kind of popular example of this maybe is SweBench or SweBench Verified,
Hmm.
where these are like actual GitHub issues and PRs, that you and tests that you're measuring AI systems against. I think there's a real trade-off here where, on one end, yeah, you get this granular understanding, and then on the other, it's really easy to interpret what a certain, success or failure, means. It's like, okay,
Yeah.
yes, it can do this thing in the real world that I understand. I have some intuitions about, um, yeah. So I think there's a real trade-off. Um, I think that like, yeah, what do I think here? I think it's really hard. I mean, broadly, I feel pretty pessimistic about this like kind of granular like approach.
Hmm.
Um, I think maybe this like has something to do with the amount of systematicity in neural networks themselves or something, where it's like, well, you know, like they are just kind of inconsistent, but are still capable of really impressive things,
Right,
often.
right.
And so like maybe you just can't get like this kind of like extremely crisp understanding, and you just have to, kind of aggregate or look more broadly at like things that actually, are relevant for your kind of decisions about whether to deploy a system or how safe it is or whatever.
Mm.
I think that's probably like where like the direction I lean in or something.
Yeah, I also wonder if there's something along the lines of like often these sort of high level things. So take like something like economic growth, right? It's an aggregate of like a bunch of things a bunch of people are doing. It's like not very well isolated, and also it's like relatively smooth and predictable. Like not
Yeah.
totally, but like it's pretty smooth, right?
Yeah.
So like time horizon, you might not have thought that it would be this nice trend, but it is.
Mm-hmm.
It's sorry. Part of the reason, okay, I'm going to tell you about a book that I'm reading. Part of the reason this is on my head is that I'm reading this book, Inventing Temperature,
Ah, yeah, yeah,
which
yeah.
yeah, it's very popular in these like less rung spheres, and I'm finally getting around to it. And
I haven't read it yet, but I've heard lots of great things about it.
well, it's
Yeah.
great. I'm gonna spoil it a little bit, right?
Okay,
So
that's
like,
fine. Yeah.
so the first chapter is basically about the problem of like, suppose you want to have a thermometer, right? Um, uh, like, suppose you want to standardize a temperature scale that all these thermometers use, right? In order to do that, you've got to find some phenomenon that's like always the same temperature, but that's repeatable,
Yeah.
that a bunch of different people can use,
Yeah.
right? So, firstly, there's a bit of a weird circular thing where you have to know that a phenomenon always has the same temperature before you have a thermometer, right?
Yeah.
Which like, okay, maybe you can use the same thermometer and do it multiple times, and you just trust that like volume of the mercury or whatever is like a good proxy for the thing you want to talk about as temperature. Um, but so one funny thing is there were initially people were just like really wrong about what could possibly work for this. Like you have people saying like, what if we do like the hottest it gets in summer, or like
Mm.
how cold it is
Whoa.
underground,
Yeah.
right?
Oh, that's
And it's
great.
like,
That's so good.
yeah,
Oh my
it doesn't
God.
quite
I love it.
it doesn't quite work, right? But eventually people are like, oh, we're gonna use boiling water, right?
Mm-hmm.
Now, firstly, like we now know that the temperature that water boils at depends on the atmospheric pressure, right?
Yeah.
Well,
Yeah.
luckily they knew that as well, so they were able to control for that.
Oh. Okay.
Um,
Cool.
but you ever like
How do they know that? Does the book talk about
I
that?
don't know. It's
Okay.
a up to so I've only read like most of one chapter or something, but the like I think you can do a thing where like you like especially if you're looking at temperature as a proxy for like volume of a liquid thing, and you're doing like a lot of your thermodynamic knowledge comes from stuff like brewing or engines or something. You end up in these situations where you have things at different pressures and different volumes, and like
Yeah.
I think that's the kind of thing that you can figure out,
Okay.
especially if you have this identification of temperature with like volume of a thing. Um,
Uh-huh.
but like volume of a thing under fixed pressure and fixed conditions or whatever. Um, so the so it's like okay, boiling water, right? Um, have you ever like do you like cook pasta? Where
Sometimes.
like
Yeah.
yeah. So one thing you'll notice is that like there's like first the like bubbles start appearing,
Yeah.
and then
Yeah.
you start getting a bit of a boil, and then you start getting a rolling boil,
Yeah.
right? And there are like different like the temperature of the water is different at different
Yeah.
points of this, right?
Yeah.
And also the temperature of different bits of the water is different at different points of
Mm-hmm.
this,
Mm-hmm.
right? So like what are we talking about when we're talking about boiling temperature? And like if you look at the cover of the book, it's this picture of an early thermometer that has like one line for like mild boiling and one line for like
Hmm.
it's really solidly
Yeah.
boiling vehemently, I think it
Yeah.
says.
Yeah. Oh,
And like
nice.
these are different temperatures, right? And so like so there's this one scientist who does this approach of like, okay, like what are we talking about boiling water? Like he has this theory that like one thing that happens with like fake boiling is that water has like little bits of air in it, and those little tiny air bubbles, like you start getting evaporation into that air bubble,
Mm.
and then like that air bubble sort of gets hot, it like rises up, and you start seeing vapor, but that's not like true boiling of the water.
Mm-hmm.
That's only there because there's like these impure air bubbles.
Hmm.
And so he starts going down this line of work of like, okay, let me isolate out all of the like random little things, right? We're gonna have as smooth a
Yeah.
possible surface as I can. We're gonna get rid of all of the air bubbles, And basically the thing he discovers is superheating, where it turns out you can get water like
Mm-hmm.
way above 100 degrees Celsius
Yeah.
before it actually boils,
Whoa.
right? Um, and it turns out, so basically the thing they end up doing is the answer turns out to be that water vapor is at a very consistent temperature, even when the temperature of the water is not at a
Yeah.
very consistent temperature.
Yeah.
Um, but the reason that's true is precisely because there's a bunch of just like dust in the air. There's little things that things can nucleate around, and that stops vapor from getting too hot or too cold
Oh.
before condensing.
Yeah. Oh,
And like,
interesting.
if you, and in fact, have you heard of like cloud chambers?
No.
So they're used in particle physics, and basically like what they have is they have this like super cooled vapor. So it's vapor that is under 100 degrees Celsius
Uh-huh.
that is sort of ready to condense, but doesn't have a thing to nucleate around.
Huh.
But if you like shoot a particle in it, it like condenses around that, and so you can like see the trail.
Oh, cool.
Well, like in thermodynamics, right? There's this general thing where like if there's a bunch of like random messy stuff, that produces a bunch of like observable regularities at like a somewhat higher level,
Yeah.
right? So like we have this in thermodynamics. It seems like we kind of have this in economic growth.
Uh-huh.
And part of me wonders
Yeah.
if like that's kind of what's going on in like how we should
Yeah.
understand neural network capabilities. Or maybe I just read a book and I like it.
No, I love this. Yeah. I think this is this like general idea is like super interesting. I mean, yeah, there's like, another model you could have for models or yeah, for like AI systems like how they're performing on tasks is you could imagine that there's something like a kind of constant failure rate
Mm,
that AI systems have as they're attempting tasks, and
right.
different tasks might have like different failure rates, which and so that kind of complicates things.
And by failure rate, do you mean like per time a human takes to do it?
Something like that. Yeah,
Yep.
exactly. Toby Ord actually did some analysis or some kind of follow up work
Yep.
on the time horizon paper where yeah, if you assume this like kind of constant hazard rate or yeah, per time that people spend, there's some percentage chance that the AI system is going to make some kind of catastrophic
Mm.
error and then ultimately like not succeed at the task. Then this also is like a good predictor um uh of AI system success and failure on our tasks as a function of the length of task for humans. We in our paper we used like a logistic fit, but assuming a constant hazard rate, you would use an exponential
Yeah.
fit.
I
And
do think that Lawrence Chan had a response to that, which said that like logistic fit was in fact better, and like
yeah,
even though it used more parameters or something. I
yeah,
remember a
yeah.
response along those lines.
Totally. So we did explore like different fits, and logistic was a better fit. I don't think it's obvious like how or like um I think because, for example, because of this aggregation of like maybe different like distributions of tasks, I don't think it's obvious like maybe how much we should weight, the exact quality of the
Mm.
fit versus like kind of priors on like simplicity or like yeah, this is a nice model, maybe I don't know how much to weight that. But I think stuff like this to me is like very very interesting in terms of like kind of understanding capabilities. I think, yeah, I do kind of feel like um I've really often, yeah, felt like getting at something more like the intrinsic number of actions needed to complete a task
Mm.
feels to me like intuitive, and I think yeah, other folks I've talked to like feels like a really nice kind of thing that could could be useful for understanding this. It kind of you can imagine it like slotting well with this like constant hazard rate
Mm.
model where it's like for each action that you need to take or something. But actually operationalizing this I think has been tricky. Like we've done some analysis of this, and it's been kind of difficult to like extract like really good insights. But
Yeah. So okay, I think we're currently on a tangent from a question I was asking a bit ago, which is or I think I took us on a tangent, which is like in like 2 years from now, do you think
Right.
we're still
Right.
using something like
Yeah.
time horizon? And I think like so one big response you had is like, well, will we be able to like will it just be infeasible to like
Hmm.
actually measure these time horizons? I'm wondering, so setting that consideration aside, I'm
Yeah.
wondering if you have a sense of like this is probably just the thing that's going to continue to be more robust, or like probably we're going to come up with like number of actions model or like something that incorporates the like messiness results or something kind of like that.
Yeah. I think my guess is my best guess is like we're gonna keep using it, assuming we're able to like kind of continue estimating it in a way that like we feel confident in.
Mm.
I think my best guess is we'll use it with like kind of different I don't know, different like weightings or like multiples or something based on some of these other factors.
Mm.
But I guess yeah, to me I think I've become more pessimistic about yeah, figuring out things like number of actions. It's not to say I mean I'd be super excited about that, and I don't know, I think there's a decent chance I'll like take another stab at it or something
Mm.
at some point. Uh
I wonder if
but yeah.
one like okay, here's one. Suppose we think that like yeah, economic relevance, like trying to mimic real world utility, is just like the thing. One thing you could imagine doing is like we're just going to figure out like what the market rate is to get someone to solve this task, right? Which
Mm,
is like a mixture of expertise and
yeah.
time taken.
Yeah.
I wonder if do you have a sense of whether that would end up being a better predictor?
Yeah, it's a great question. I think we have looked at this, or like tried to kind of estimate this by like kind of clustering our tasks. Yeah, I shouldn't speak too much to the details because I can't remember exactly what we did, but
Mm.
yeah, something like yeah, exactly. Just look at like these tasks are like really hard ML tasks, and so they're going to be more expensive, and these other ones are cheaper. And yeah, there's some trade off. I think I think something like that could be could be reasonable. I mean, I guess the reason why or like a reason why you might not expect that to work is that AI systems broadly have a different capability profile than people.
Yeah.
So if the year if it was like I don't know, like 1920 or something, or actually let's say like 19 like 50 or 40, like maybe like right before we had like calculators.
Mm.
If you were like doing this math of like um uh you know uh people how long does it take to pay people to pay like human computers to calculate the product of like 10-digit numbers that you need to do for whatever reason.
Mm.
You'd be like, yeah, that's like an extremely like hard task.
Mm.
And so AI or like machines are not going to be able to do that task for like such a long time. But in fact, pretty quickly after, like yeah, computers were able to do this very very well. And so then yeah, they're just applying this to modern systems. I think I do basically believe this actually is um like AI systems are like way better at these like at tasks that like seem to require humans like many years of like kind of intellectual
Mm.
development and labor to complete. Yeah, like they can do GPQA questions, they can do IMO problems, these sorts of things. And so I think I do view this as less of the bottleneck, basically. And I think I do view something kind of more akin to like agency, or like yeah, being which might point to the like messiness factors, or
Mm.
um yeah, that's not to say that there aren't other metrics. Maybe this is just an argument, I guess, against like yeah, like kind of expertise, or human expertise or something.
Fair enough.
Um yeah.
So, so I guess with that said, you know, you we have the we've got the time horizon stuff. We have H cost. I'm wondering, like, what? Yeah, what to you? What are the open questions, and like what kinds of things might I see out of Meter in the next year or so? like pushing this research direction forward?
Yeah, great question. So broadly, I think there are, I mean, there are a few things. So one is kind of continuing to use this methodology. You know, uh, currently models can do have 50% success rates on these like 2-hour tasks. Like GPT-5 I think is like 2 hours and 15 minutes or something.
Mm.
It's the time horizon. And you know, if we really are on this 4-month doubling time trend, that's like, we're at like 4 hours by the end of the year, like 8 hours spring of next year, 16 hours like fall next year. That's like not that long. And yeah, like we have fewer longer tasks, and we have fewer baselines on these longer tasks because they're more difficult to baseline. You have to find like people with like more specialized expertise, and they're more expensive, and people fail more often. And so kind of extending our task suite, and trying to just see, does this trend continue, is like one big direction. And I think there are like kind of open questions around how do we actually like affordably continue doing this. Are we like pulling tasks, or harvesting tasks from existing work that people have already done? Are we creating new tasks and then using like LLM evaluation, or like more like manual review to evaluate success on them? Are we doing other things? So I think things kind of in that direction. That's like one class of things, kind of trying to continue this basic methodology. I think there's like another kind of class of directions that we're pretty excited about, which is something more like we have this like it's like kind of like what I just described as something like benchmark development,
Mm.
and then like like evaluating models on these tasks. But then there are a bunch of these questions around how good are our benchmarks? How good are other benchmarks? So I don't know. Yeah, over the past couple weeks, I've been like labeling like many dozens of like attempts of models on SweBench with like a bunch of different factors to try and understand, like, okay, for example, just uh, you know, how good are our tests in SweBench? Like, are models often implementing correct functionality that isn't captured by the tests, because the tests were kind of written for the specific implementation that the human originally wrote?
Mm.
Or alternatively, are models often succeeding, but as judged by the automatic test cases, but they're actually they actually like break a bunch of other code that isn't tested in the repo, or like their solution is just so bad in some other ways or something that we wouldn't actually call that like a success. So kind of broadly, this is like one example of this kind of stream of work that we've started doing more of over the past few months, of kind of trying to understand benchmarks, the science, this kind of like science of evals stuff, like how can we interpret certain scores on different benchmarks, ones that we've made, ones that other folks have made. Um, Also questions around kind of to what extent are current methods for improving AI systems like going to generalize. So one example that comes to mind of an open question, I think, to us, is something like training models on verifiable, formally verifiable tasks, like passing test cases. Uh, uh, there, people talk about like reinforcement learning from verifiable rewards. There's a question of like how much progress currently is coming from this,
Mm.
and maybe there are like two subquests, or like two like corollary questions, like how much should we expect progress when training in this way to like generalize to non-verifiable tasks, or tasks that are messier, or more qualitative. And then alternatively, maybe if improvements in models from this type of training doesn't actually generalize well, like what is the kind of how much human data, for example, do you need to train models that are good, like on like more qualitative, like messier tasks. So trying to get some kind of sense of things like this. I think like this is something we're interested in. Yeah, the exact projects that I think we'll end up doing, will depend on specifics, but
Fair enough. So if that's things that Meteor might end up doing, there's a whole other world out there, including listeners to this podcast.
oh,
What should if they're interested in like advancing this research direction, what would be good things for outside people to do?
yeah. So one thing that I've been really excited about is this work, or basically kind of making it easier to run evaluations in kind of standardized ways.
Hmm.
So this that we've at Meter we've started using this platform for running evaluations called Inspect. That is open source. It's kind of primarily developed by folks at the UK AI Security Institute. But this platform is great, and there are like a bunch of benchmarks that have been implemented in it, and I'm super excited for like more benchmarks to make it in, and to kind of improve the like I don't know, the ecosystem's like ability to broadly run these evaluations. That's like kind of more on the like engineering side of things. I think in terms of research, I'm excited about people extending the time horizon methodology to kind of more benchmarks. So actually someone this guy Sean Peters, I think his last name is,
Hmm.
he kind of evaluated models on like cybersecurity benchmarks in particular, and like used kind of time estimates from those benchmarks, or I think he did some amount of estimating task length himself, and fit some trends to models performance on these this particular kind of slice. I thought that was like a really useful way of just kind of getting more data, validating these things. So I think I'm like excited about kind of direct follow up work like that. I think there's like something in the vein of or like directions in the vein of kind of what we talked about of trying to decompose model success and failure, or like understand like what are the fundamental trends going on here. I think like I said earlier, I was like pessimistic about these like extremely like kind of constrained, like less realistic
Hmm.
types of tasks, but I do still think they can be like quite useful for just like almost as like diagnostics or something, like just like kind of helping bound like our understanding of what models can and can't do. Something that comes to mind is people have made kinds of tasks that are basically just like how many of like a very kind of basic action can models like take in a row before they like fall over or like get off track. So things kind of that nature, like very very large like kinds of arithmetic, that comes to mind as an example. I think things like that are actually like interesting, although I think they're like they're more to me like kind of bounding model capabilities or something.
Fair
Yeah.
enough. So the second to last question I'd like to ask uh, is there anything that I should have asked that I haven't yet?
Great question. Yeah. I mean, I think like broadly, we've touched, we've talked, we've covered, a fair bit of meters, like capability evaluation work. I mean, I
Hmm.
think there's like, there are kind of big open questions to me around, like how long we'll be able to continue doing this work.
Hmm.
Not even just from a tractability perspective, but also just from a like like, will it actually be useful perspective for in particular for estimating risk. So like at a certain point, if we are seeing that AI systems are able to do AI research very effectively, then there's this then it's like, okay, well, how do we continue estimating risk? Is risk just like maximum? Like probably not. Like people are still going to be doing kinds of monitoring, or I expect folks to implement kind of basic kinds of like control methods. So kind of we've started over the past few months. We've been kind of doing more work trying to kind of create better metrics for things like monitorability. I guess I'm kind of just describing this as less of a question, but I don't know. I think I haven't been working on it, but I think it's like very very interesting and exciting work. Yeah.
Yeah, sounds cool. So speaking of, if people are interested in following the work that you and your colleagues at METR do, how should they go about doing that?
Yeah. So going to our website, meter.org. We publish our research updates there. I think that there's a way of you can put in your email and subscribe. We also post on Twitter. Meter_evals, I think, is our is that I can't remember our Twitter handle. Anyways,
It'll be in the description.
Yeah. And we're also hiring. So we're hiring experienced researchers and research engineers. So if that's you, definitely reach out, and we may be excited to chat.
Great. Well, thanks very much for coming and chatting with me.
Yeah, thanks a lot for having me. This was really fun, Daniel.
This episode is edited by Kate Brunotz, and Amber Dornace helped with transcription. The opening and closing themes are by Jack Garrett. This episode was recorded at Far Labs. Financial support for the episode was provided by the Long-Term Future Fund, along with patrons such as Alexei Malafeyev. To read a transcript, you can visit axrp.net. You can also become a patron at patreon.com/axrpodcast, or give a one-off donation at ko-fi.com/axrpodcast. That's ko-fi.com/axrpodcast. Finally, you can leave your thoughts about this episode at axrp.fyi.